Welcome back. In this lecture, we will see all the primitive types defined in Java. There are 8 primitive data types available in Java. Byte, short, int, and long are of integral type. Float and double are floating point numbers. Char is for textual data, and boolean is for logical conditioning. Let us first see byte. The byte data type is an 8-bit signed integer. Signed integer means it can store positive and negative numbers. Out of 8 bits, 1 bit is used to store sign, positive or negative, and 7 bits are used to store data. It has a minimum value of -128 and a maximum value of 127. For example, following 3 statements will compile without any error because all the 3 values are within the range of byte. We specify the type first, then the variable name, and then the literal value. So B1 is going to store -128, B2 will store 127, and B3 will store 25. Let us see an example. I have created another project with the name primitives, and inside that I had defined byte primitive 1 class. In the literals chapter, we had seen that integer literals can be represented using decimal, binary, hexadecimal, or octal form. These 4 variables B1, B2, B3, and B4 are all assigned the value 25. Let us now see how these values are stored in the memory. Let me first expand the working area, minimize Package Explorer. We need to first calculate binary value corresponding to decimal 25. Here is a way to convert decimal to binary. First we write a decimal value which is 25, then we'll start dividing it by 2. 12 times 24, remainder is 1. Again divide by 2, 6 times is 12, remainder is 0. Again divide by 2, 3 times is 6, remainder is 0. One more time, 1 time, remainder is 1. And now we cannot divide further. So we need to start from here and go up. So the binary value corresponding to decimal 25 is 1, 1, 0, 0, 1. Now let us store this value in the memory. So we have a variable with the name B1. Let us specify the memory space first. It is of byte type. That means it can store 8 bits. Name is B1. At the time of storing, we'll start from rightmost end and we'll move to the left. 1, 0, 0, 1, 1. Leftmost bit is known as a signed bit, and this is a positive number, so we will store 0 in it. So 0 is for positive, 1 is to represent negative, and the remaining bits we will fill with 0. So this is how decimal 25 is stored in the memory. On the similar lines, B2 is also stored in the memory. This is B2. Now it is a bit cumbersome to find out binary values. So to understand the concept better, we will be directly using decimal representation. So let us now use decimal representation for B3 and B4. So suppose this is a memory location for B3 and this is the memory location for B4. So B3 also stores 25 and B4 also stores 25. Let us now execute this program and check the output. Control F11. So all the 4 statements are printing 25. Let us see one more example to store negative byte values. In this example, I have specified -25 to all the 4 variables. Let us see how negative numbers are stored in the memory. We first need to calculate the binary value corresponding to the positive number. As we had seen in the previous example, decimal number 25 is equals to 0, 0, 0, 1, 1, 0, 0, 1. To find out the binary value for -25, we first need to flip the digits. So we'll change 1 to 0 and 0 to 1. This becomes 0, this becomes 1, 1, 0, 0, 1, 1, 1. So in this step, we had just flipped all the digits. Now add binary 1 to it. So the rule for binary mathematics is 0 plus 0 equals to 0, 0 plus 1 equals to 1, 1 plus 0 equals to 1, and 1 plus 1 equals to 1, 0, which is decimal 2. So let us now add binary 1 to this. 1 0 is 1, 1 0 1, 1 0 1, 0 0 0, 0 1 1 1. This number represents minus 25. Note that leftmost bit is 1, which represents a negative number. To store this value in the memory, let us first assign memory for variable b1. Type is byte. It can store 8 bits of information, and it is storing 1 1 1 0 0 1 1 1. Similarly for b2, it will also store the same value 1 1 1 0 0 1 1 1. Note that this method is known as 2's complement method. So we specify negative number in the source code file, but negative numbers are stored in the memory using 2's complement method. But instead of using binary values, we will be using decimal values for easy understanding. So for B3 and B4, we'll be using decimal representation. B3 is minus 25 and B4 is also minus 25. Let us run this program and check the output. So all the 4 variables contain minus 25. The byte data type ranges from minus 1 to 8 to 1 to 7. So the code will not compile if you try to assign any value that is out of this range. For example, 1 to 8, this is out of range, or minus 1 to 9, this is also out of range. So these two values will not compile. Next comes short. The short data type is 16-bit signed integer, so it can also store positive and negative number, and the leftmost bit is used for storing sign. It has a minimum value of minus 32768 and a maximum value of 32767. This means short can store all the data that belongs to byte plus some extra data. These three statements will compile successfully because all the three values are within the specified range of short. Let us see an example of short. Over here, minus 32768 is assigned to S1, 32767 is assigned to S2, and 500 is assigned to S3. Let us run this program and we see the correct output. As with byte primitives, if we try to assign any values that is out of range, we will get compilation error. So this is out of range value. This is also out of range value. So we are getting compilation error. Then comes int data type. The int data type is a 32-bit signed integer. It has a minimum value of minus 2 to the power 31 and a maximum value of 2 to the power 31 minus 1. This means int can easily store short data plus some extra data. For example, int I1 equals to minus 50,000, int I2 equals to 50,000, and int I3 equals to 100,000. These all three statements will compile successfully. Underscore is just for grouping purpose to improve readability. Value stored in I3 is 100,000. Let us see an example for int primitive types. So over here we have a memory location. Its name is I1. Type is int. And to make it easier, I'm going to store the decimal representation only. So at this statement, I1 stores minus 21474836648. Then we are printing this value onto the next statement. At line number 10, we are assigning a new value to the same variable I1. That means this value is overridden by the new value. New value now is, then we print the newly assigned value, and finally we are assigning 100,000 to it. So we'll delete this one and we'll assign 100,000. When we print, 100,000 will be printed. So let us now run this program. So this line printed -2147483648. Line number 11 printed positive value, and line number 13 is printing 100,000. Out of range values give compilation error in case of int as well. This is out of range, and this value is out of range on the positive side. The last primitive in the list of integral type is long. The long data type is in 64-bit signed integer. It has a minimum value of -2 to the power 63 and a maximum value of 2 to the power 63 minus 1. That means long can store all int data plus extra data. To represent a long value, we need to suffix the value with L, either in uppercase or lowercase. One important point to note here is that by default, integer, literal, or of int type, and hence for the values within int range, suffix L is not needed. But for values outside int range, suffix L is compulsory. So let us see an example. In this case, this value is well inside int range, and int can be easily assigned to long type. So in this case, suffix L is optional. Similarly with this value as well, and similarly with 100,000. In all the three cases, suffix L is optional because the literal -50,000, 50,000 or 100,000 are well inside int range. But if we specify a literal that is out of int range, we need to suffix it with L. So in this case, L is compulsory. Let us see an example of long data type. At this statement, we are assigning 5,000 to long variable L1. L is optional over here because 5,000 is inside int range. At this statement, we are assigning -5,000 to another long variable L2, and over here also L is optional. Then we are assigning a literal that is out of int range. So in this case, L is compulsory. Similarly for L4, for this value, L is compulsory. Let us see a very good use of underscores to store credit card number. So over here, L is compulsory because this value is way outside range of int type. So this value with underscores is similar to this value without underscore. Let us execute this program. So over here, L1 is storing 5,000, L2 is storing -5,000, L3 is storing this value, L4 is storing this value, and finally the credit card number is storing this value. Note that L is not shown in the output. It is only for the source code file. Similarly, underscores are also not shown in the output. This is for readability purpose only. That's it for this lecture. I'm stopping it here, and in the next lecture, we will see remaining primitive types: float, double, char, and boolean. See you in the next lecture.